Hi there, today we're looking at Synthesizer Rethinking Self-Attention in Transformer Models by Yi Tai, Darabari, Donald Metzler, Da-Cheng Chuan, Zhe Zhao, and Che Cheng. These people are of Google Research, and on a high level, they're trying to replace the self-attention mechanism, which is currently a dot product mechanism in a transformer, by a sort of a learned attention mechanism, therefore eliminating this expensive dot product. And they test the model and conclude that it sometimes works a bit. So the results are sort of inconclusive, but that's the paper on a high level, and it's fairly cool to go through. And as always, if you like content like this, consider subscribing and sharing it out. All right, so they say the dot product self-attention is known to be central and indispensable to state-of-the-art transformer models. So if you don't know what a transformer is, it's best I made a video on the Attention is All You Need paper, and that explains what a transformer is and what an attention mechanism is in detail. But they are right. Of course, the attention mechanism that is via the dot product of queries and keys is pretty much what makes transformers transformers. And they here ask, is it really required? Which is a bold question in light of that, right? They say they investigate whether or not you really need this, and they say via extensive experiments, we find that first, random alignment matrices surprisingly perform quite competitively, and two, learning attention weights from token-token, that means query-key interactions, which is this dot product interaction, is not that important after all. Okay, they proposed this new model called Synthesizer, a model that learns synthetic attention weights without token-token interactions. Our experimental results show that Synthesizer is competitive against the vanilla transformer models across a range of tasks. Okay, so let's dive in. So what is different here? They're basically saying, look, in each transformer layer boils down to something like this, where you have an input sequence X right here, and you want to get an output sequence Y. And in order to do that, you need some sort of this thing, which is the attention matrix, multiplied by this thing, which are called the values. And we'll explore that a bit deeper over here. So in these transformers, it's always kind of helpful to visualize yourself the input sequence as sort of nodes, and so this would be one layer. We have a 5 length sequence, and we want to transform it into the next length 5 sequence. And maybe it even helps to label maybe like A, B, C, D, E. You can just imagine kind of these. Of course, as you go up the layers, it doesn't necessarily always correspond to the same input token, but the position labeling them is still, it's pretty helpful, I find, especially for, things like BERT or something like this. So you want to transform the sequence that's incoming here into another sequence, and the basic mechanism in a transformer, if you go up the layers, is the routing of information. So you want to route information around the sequence, and basically such that at the end, the whole sequence knows about every word in the sentence, knows about every other word that there is in the sentence, knows about the associations between the other words and so on, such that you gain you start out with individual words, and at the end what you want is sort of that every word has a pretty good idea of what's going on with every other word, okay? And that's why you continuously, as you go up the layer, route around this information. Now the question is, how do you route this information? How do you know which word goes to which other word? And here, maybe the sentence starts with the word, let's call Sarah, okay? Sarah, and then it goes on, and at some point it says she, okay? So she is the pronoun, and we can also label these Sarah, she. So if we think, how do we route information, it would be beneficial for us if the information that there is a word Sarah here in the sentence would be routed to the word she, because the word she, it's a pronoun, it knows I'm a pronoun. And if there is like a person in the sentence, that would be valuable information for me, like to know what's kind of going on and to understand myself better. Basically, every word wants to understand itself, and it kind of calls out for information from the other words. In a transformer, this is done via what this paper calls this dot product attention. And that's the following. Every word, every token emits what is called a key and a value. And the key and the value are just two vectors. So every word is going to emit two vectors. I'm going to draw one at the bottom here, and I'm going to draw one at the top, okay? Like that. So you can imagine the key as sort of the word advertising what it is to other words. And so these are the keys down here. And the top, I think I called it value. That's wrong. It's called a query. You can imagine the query as a word describing what it wants from others to know, okay? So in that case, you'll see that the vector here and the vector here, these are now routed by dot product. So the ones that align in the dot product, in the angle, they will be routed to each other. So this would be routed here, and maybe, okay, I drew this. This one would be routed here, and the others would be kind of routed a bit here and a bit here maybe. Okay, it gets fuzzy, but you get the concept. But in order to do that, you basically need to put the dot product from every single key with every value. Query. And that gives you basically this quadratic dot product that these transformers have. And that's expensive, okay? So they have a little picture here. This is what a vanilla transformer does. Every input here emits two things, a query and a key, and then there's the dot product attention to decide what's this attention matrix, okay? Now, this attention matrix is then used to aggregate these values. So actually every token emits three things. Also this value here, which is basically, it's not that important, but this just describes the information that you want to pass on to the next layer. And then it goes through this routing right here that routes the information to the correct output places, and you get your output. Now, what they propose is something different. They propose this dense synthesizer right here, where instead of the dot product attention, every single input here emits basically a row of this matrix directly without having to go through the dot product. Now, it helps a bit if you imagine it in our little framework here. So let's draw this again. And let's see what these synthesizers. By the way, they call this the dense synthesizer because they have another variant as well. Okay, here is our sequence. The lower layer, we want to transform it in the upper layer. This is the Sarah node, and this is the she node. Sarah, she. Okay, so how do we route information now? Wow, okay, I missed that. In the dense synthesizer framework, every token just gets to output, basically it already gets to output where it wants information from. So every single token here gets to output where it wants information to come from. And by where, because in the original transformer, the where was basically defined by these inner product. Now the where is just defined by the position, okay? So it just says, I want information from position 2 and 3. Or this node here could say, I want information from position 5 and 3, okay? And this is dependent on which token there is. So each token looks at itself. And in the case here of she, you can imagine this token says, well, I'm a pronoun. Therefore, I may be referring to a person. And I know that in the English language, a person is often at the beginning of the sentence. And therefore, I certainly want information from token from position 0. It doesn't see that there is this word Sarah here. It simply can see only the positions 0, 1, 2, 3, 4. Okay, so it will basically output, each token here will output an L dimensional vector, and L here is the length of the sequence. An L dimensional vector that already defines the distribution of how you want the information. So I want lots of that and then not much of that, and maybe it wants a bit of that and then not much of that. Okay, so each word up here is going to emit this L dimensional vector. Okay, so each word, each token decides for itself where it wants information to come from, based purely on what the token itself is. Okay, and of course in the higher layers, this information, like the information of what the token is and what else is there, gets aggregated, and that's how computation happens. But in a fundamental level, each node looks at itself and decides, where do I want information from, just given what I am and not what others are. So this results in you not having to do this dot product attention. But of course, you lose the information of what's down here. You simply go on the positions of the nodes. And they formalize this like this. So they basically say, okay, each transformer mechanism needs some sort of a softmax over this matrix B right here, which this is this routing matrix. And then g of x is just the values of x. So g is often just a linear function. And they say, well, this B here in the classic transformer is computed via this dot product attention. Can't we just simply have a function right here that just outputs the B given an x? So, and it's, you see here, xi refers to one row. So x here is an L by D matrix, and they say the sequence length is L. So if you imagine this, this is the sequence length, every xi is a vector here of dimension D, right? Sort of like a word embedding. Okay. Now, what you want to do is you want to take each individually, run it through the function f, and then get out an L dimensional vector. Sorry, an L dimensional vector. This is of dimension L. And if you do this with with all of the x's, right, you'll get an L by L matrix, which basically is now your routing matrix. It tells you, so this thing tells you that this particular piece in the input sequence wants how much information from this particular piece in the output sequence, or vice versa. See, this is the problem here. They don't really specify this B, how this B matrix will be composed from the BI. Like, is BI a column or a row of this B matrix? I don't know. And therefore, it could actually be the other way around, that the information, that it's not the sort of the tokens deciding where they want information from, but it could be the tokens deciding where they want to send information to. But just from the notation, I can sort of guess that it's the way that I described right here. But I hope you see the difference here, right? Before we had this dot product attention. Here, each of these columns basically is an independent evaluation of this function that only considers xi and doesn't consider any of the xj that it wants information from. It simply goes by position. And they use this basically this one hidden layer neural network right here, two weight matrices and a nonlinearity, a ReLU nonlinearity. So they replace the dot product by simply learning what the attention pattern is going to be per individual token. Okay, now they do it one step further. They say, okay, so we've already lost the dependency basically on what the input sequence tokens here are. Can't we also just kind of lose the dependency of what the output token sequences here are? So what they propose in their second variant, this random synthesizer, is the following: is, hey, why don't we just learn how the information is going to be routed, irrespective of which tokens come in, right? We're just going to learn this, and it's going to be one routing pattern for all of the possible input-output sequences. It's just going to be this routing pattern. So they have actually two variants. First, one where it is really just random, like they just leave it at random and they don't even train it, and the second one where they train this thing, but these things now have nothing to do with the tokens. They're just fixed, and they are just global. So this would directly be, you learn this L by L matrix. And yeah, so if this strikes you a bit in an odd way, because you kind of lose the dependency on your data in this routing pattern, and it's not really routing anymore, right? And if you think that you've seen this before somewhere, and you think, hey, that looks like a feed-forward layer from like your very first MLP, then you would be absolutely correct. And I'm not sure why they don't point this out. I have a really hard time believing that they themselves tricked them into such a thing right here. And so I can actually show it, right? So the question is, how is this here, this dense synthesizer, is this still different or the same as a feed-forward layer? And is this different or the same as a feed-forward layer? So if you do the math, say, and you look at what a feed-forward layer is, in a feed-forward layer, yi, right, my ith entry in the output is going to be a sum over all the inputs xj multiplied by a weight ij. Okay, so whenever I can represent something in this fashion, where I have a sum and then I have like a fixed weight, and that I learn, and that has nothing to do with x, that is not dependent on x, multiplied by x, then it is a feed-forward layer, basically, or like a fancy feed-forward layer. So let's look at the dense synthesizer. What does the dense synthesizer do? The dense synthesizer says yi is equal to a sum. Okay, we're starting off well. And so it says g of xj, right? But this g usually is just a weight matrix where we compute the values, right? We said this was the values of x. So g is usually just a matrix. Let's call it wv. And then here we have like some softmax thing, right? We have some softmax, and the softmax is going to be over this dense pattern right here that we described, here. And this pattern is going to be f of xj, right? So, no, xi. F of xi. Is that correct? Xi, and here is a j. Maybe. Yes, that's correct. And f, okay, it's like it's two layers, but we can basically say it's like a weight matrix, because ultimately, if we learn a neural network or a single layer, it doesn't really matter to the discussion here. So let's call this WBXI. So you see right here, we do have a weighted sum over the xj's, but the weight that the weighted sum is using is dependent on xi right here. And therefore, you can't you can't represent this as just a feed-forward layer right here. Of course, if you have the full dot product attention, then in here would actually be a dot product between xj and xi, right? So xj transposed xi or something like this. So what about this random synthesizer? So the random synthesizer has yi, has a weighted sum over this wv right? That's the values, softmax over this matrix R. And R is simply this L by L matrix right here. Now you can immediately see that this part right here is static. It doesn't depend on any x, and it is learned as a joint function, right? So this, if I just call this wij, then I'm back to my formulation, right? Sorry, ij. Then I basically have my feed-forward layer. So the random synthesizer is just a fancy way of writing a feed-forward layer. Now, of course, if you're going to have the softmax, you maybe have some different inductive biases in learning it, but ultimately it is a straightforward feed-forward layer. At least that's what it looks like to me. I'm very open to be convinced otherwise. Okay, so they have this drawing right here. On the left, you see the vanilla transformer, the dense synthesizer in the middle, where you kind of learn how to produce this matrix and then route the value through it. And on the right, where you simply output this in a learned or actually completely random fashion, and then route your values through that to the output. Okay, now the question, of course, is, okay, they also do factorize it, but this is not really the, this is more of a point where now you can actually, if you have such a matrix or you produce such a matrix, you can then factorize it into sort of lower dimensional matrices. And that is, first of all, to save space, and it is also a regularizer, because what you're essentially saying is you're applying an inductive prior to say, I think these matrices have like some low-level structure to them, and if you factorize them, that's a prior on that exactly. So you can factorize the dense and the random synthesizer into smaller matrices, and that will save you parameters. And you can actually also mix too. So you can, for example, mix the random and the dense synthesizer. Now you have to pay attention, it's not like an interpolation. If you mix random and dense, you will have to learn the parameters of the random and of the dense synthesizer. So that's going to be like strictly more powerful than either one alone. They list everything here where they say the standard dot product attention. What we have is we have this formula right here. You can actually formulate it in their framework. You condition on all the xj for any xi, and see here, I wrote this as xj. I was dumb. It should be the entire x. And there is interaction between the tokens, and it's going to cost you 2d squared parameters. Now, parameters is different from computation. Which if you don't do the dot product, you also save a bunch of computation, but here they look at a number of parameters. So in this random synthesizer, you simply output this matrix R. It's global, there's no interaction, and it's cost you L squared memory in L squared parameters. Now often in these models, L and D are actually pretty similar. So L might be something like 512 tokens, the length, and the dimension right here might also be something like 512. So per se, this is not really a saving in parameters. Only when you go to the factorized models right here can you bring in this k, and k is this lower dimension of factorization, and if k is much smaller than L, then you save a bunch of parameters. The dense synthesizer formula is like this. This is how you produce the attention matrix. You condition on xi, but not xj, right? For each yi, you condition on xi, and you do not care about the xj's. That it is local. That means it depends on xi, so the routing actually depends on the information that goes through, but there is no interaction. And you're going into d squared plus dl, which is also pretty much 2d squared, right? And or you go to this lower number here if you choose a good k. All right, now experiments. So they apply this, and we are absolutely stoked how this is going to turn out. So they go on machine translation. Now, okay, before we go into the results, do you think machine translation is a good or a bad task for this model? Okay, I think it is a good task for this model. It's a very favorable task for this model. Why? Why is machine translation a favorable task? Well, mostly in machine translation, if you think about how information is routed. So I have a sequence of German, let's call it, or English, let's call it the dog barks. And I have a sequence of German, der Hund bellt. Come on, Hund bellt. Now, okay, first of all, I know they are only talking about self-attention, so this example here actually makes little sense in the actual practical applications, but I just want to demonstrate why machine translation specifically has... So how would you route information here if you have to route information between the two things? What you would do is pretty deterministically do this, right? So in machine translation, what is very, very, very often the case is that mostly you're going to align the positions in the same way, independent of the input. Specifically here, you would always, most of the time, align the beginning with the beginning, the end with the end, and so on, because for most languages, especially similar languages like English and German, the order of sentences and number of words per thing you need to express is going to be roughly the same. So if you did not know about what the sequences were, or you only knew one of them, like you only knew there, and you have to guess where should information come from. Well, I know in English you also start with like this, what's this called? An article? Yeah. Yes, this is an article. Showing my linguistic skills here. You would also start with that, right? You would say, I want most information from position 0. Obviously, I don't care what is there. So and again, I know they'd only do it in self-attention, so it actually makes no sense that I have two different languages here. But machine translation is probably a task that lends itself very much to sort of globally learned or only partial observably learned attention patterns because of the nature of the task, right? So let's keep that in mind and go to the results right here. Now first of all, what they do is they list the original transformer paper, and actually have it here because they have this same experiment. Now, this is the kind of transformer we're talking about right here. And it is notable that this paper only proposes to replace the self-attention. That means the attention that would be within one of these two columns and not the attention that goes across from the left to the right, right? But still, you can see that the attention that goes from the left to the right, then in the next layer is going to end up as self-attention information, right? So I think my argument still counts in this case, in the machine translation case. All right. So they have this same experiment right here. Yes, they have English-German translation, and they their base model gets 27.3, and that's what they evaluate right here. They list this 27.3. But they also say when we train it, we get a bit of a higher number, 27.67. And especially on English French, they get a higher number than that. But let's stick to English German for now. Now, they also do language modeling, which the original paper didn't do, and record the perplexity right here. Okay, so the first thing they point out is if we train the synthesizer with a fixed random matrix, that means we just put a random routing and we do not ever change it. What's there to learn? So if you want to learn something in the transformer, there's still many things to learn. There's the feed-forward layers, right? There is the value encoder and so on. So it is reasonable to assume that the transformer could sort of learn to just handle the routing pattern that is in place, and that the rest of the model can sort of absorb that shock. And interestingly, you get onto 23.9, so almost 24 blue points. And I mean, it seems they point out that it's fairly close. If you look here, this 24 is actually pretty far away. It's the worst baseline right here in the original paper. This ByteNet had this 24 blue. I mean, I guess it's cool to point out that it works as such, but you know, in these tasks, actually many things work, right? With if you distill this down to some sort of a bag of words model and so on, I'm pretty sure you can get pretty good results as well, and you can get you can go to 24 blue. I have no clue of this field, but I just want to point out, just because the number is in the same ballpark doesn't mean that it is very astonishing. It's maybe just you have so many parameters that the rest of the model can sort of absorb this the shock of not being able to learn this, and can just handle whatever pattern you put there. It can just kind of work with it. Okay, that's many people have observed, if you like put just random junk in the lower layers of a CNN, like random filters, and never train them, you can still the rest of the network can adapt. So that's basically this effect right here. I don't think it's a testament to we don't need the dot product attention. It's more like this just happens in deep learning. Then, however, they say if we now learn this one matrix, so we learn this routing, but globally, we get into 27.27 blue. And this already seems fairly close, right? And you mainly need to compare with this number right here, because that's actually the same training run and so on. So, but still, it is quite a bit away. It's 0.4 blue points away, and that is a sort of significant difference, I think. Then they go further. If they go to the dense synthesizer, you can see right here the model size is lower than this one, and they get 27.43. Now they get even closer, right? And they are actually on par if they mix random and dense right here. And you can see that it's also almost the same amount of parameters. And when they mix these random and vanilla, so what they now have is the dot product attention plus a purely global feed forward, sort of like a bias of what to route where. Then they can outcompete this original model. But also now they have more parameters, right? So this model, you would expect it to be, strictly better than either of the two alone, and it is. And it is actually astounding that the synthesizer that mixes the vanilla with the dense, even though it has even more parameters, it does worse. So with these sort of results, especially then you go fiddle with like 0.1, between this and that. I know I said 0.4 blue is a lot, so 0.1 must be something, and it surely is, but also it's it's always the question of how many hyperparameter tunings you put into something like this. And generally, you should always sort of look at this. If you were a researcher and had to put the best possible numbers here, what would you do? And then you correct for that in your mind for how much it might actually work if you were to go ahead and train that on your data. But nevertheless, it gives some cool insights, right? What I'm a bit confused by is that if you sort of look at the original paper and you look at the perplexities, and they have a table down here where they compare a bunch of their instantiations of their model, and they compare also the perplexity on a language modeling task. And the perplexity here seems to correlate extremely well with the blue score, right? Whereas the perplexity here, if you look at the perplexities over here, they do correlate, but I have the feeling they don't really correlate as much here, which sort of speaks to the fact that you're going to see in the rest of the paper that these models, they tend to sometimes be able to do well, but then other times not. And it's not really super clear when. So look at this, for example. They now apply their models to summarization and dialogue generation, right? These are two tasks where you need to output text, and you can see that the results are all over the place. So in this metric, Rouge 2, and Rouge is sort of an n-gram overlap metric between gold standards and what you produce. In this metric, the original transformer is best, but in Rouge 1, this synthesizer mixed here is the best, and in Rouge L, this one is the best, and in dialogue generation, all of them are actually not as good as this one right here, where it's just the dense, which is strictly less powerful than the ones on the bottom. But so as you can see, yeah, I think what you should take away from this is that it is interesting that it sometimes works, but it seems to be a fair bit of shakiness to these results. Okay. Now they go on and they test this on super glue, and this is a benchmark. So glue and super glue, they consist of these different tasks right here. And now we are out of the text generation game. We are in the game of, for example, you have two sentences and you need to decide which one is like, which one entails the other, or are they contradictory, or things like this. So it's more of a, let's say, a classification task, and people apply different models. So it's no longer a text generation task, so they switch model. Instead of the vanilla transformer from the Attention is All You Need paper, they now go on to the T5, the text-to-text transformer. And they simply take the architecture and they change the attention in their with their attention. And you can see right here that the results are quite different than before. So in every single case, either the T5 model, the base model with the dot product attention, is the best model, or the synthesizer but including V. So plus V means plus vanilla, means it also has the dot product attention plus this learned thing right here. Okay, so R is now the learned, I think the learned, I would be surprised if it was the random, but it could also be. But in any case, it's strictly better, right? It's strictly more powerful model. And the only way it can actually perform worse is when, it's too many parameters and so on, and they kind of take stuff from each other. And there's effects where more parameters can hurt you. But never is any model that doesn't have the dot product attention on top. And these authors here argue that this can be largely attributed to the fact that the encoder self-attention in the T5 setting also functions as a cross-sentence attention. So what do they mean here? If in the T5 is just, as I understand it, this is just like an encoder, like BERT. So imagine maybe this is BERT, right? What BERT is simply an encoder-only transformer. That means you put in your sequence, and out again comes a sequence, and you have like a special token that you use for classification and so on. So this is less when you have to generate text, but more when you want to classify text or things like this, find something in a text. And what you would do if you have two sentences, you need to decide something about them. You put the first sentence here, and then you put like a separator token here. This is usually called like a separator token. And then you put the second sentence here. So you just concatenate them, and you let them go into the transformer. And they argue that if you do self-attention on this entire sequence, then you get attention patterns like this. And this is sort of like cross-attention between sequences, right? It's not really self-attention. And that's why their method doesn't work, because it basically deals with self-attention. But I'm not really buying that argument. I mean, if this is a sequence, if this is one sequence, this is self-attention. And if you were going to argue that out of the blue, a token, in your case, like in your original formulation, can simply, just by looking at itself, know which position it wants the information from, then certainly here, this token could also learn that it wants information from over here, or from the first word here. I don't really see the difference. Maybe you need to somehow standardize where this separator token is, so that it's always in the same place, and that the second sentence always starts at the same place. But if you have that, then I really don't see any difference in the argument you can make here that this shouldn't work as much as the others. What I think is happening is that this task is simply involves more difficult reasoning, involves more routing of information, like dynamic routing that's actually dependent on what's in the tasks, rather than something like machine translation, which most of the time has some global routing bias, like some pattern that works pretty well across all. All right, so the last part here is where they kind of introspect the model. And in the first thing, they say, okay, we look at the distribution of weights. So these are the weights in the decoder at the beginning of training. And you can already see that the standard transformer weights and the synthesizer weights are different from the dense synthesizer weights are different from the random synthesizer weights. And this probably is mostly due to the fact of how you initialize, like these deep learning frameworks. If you have a matrix, they will look at what's this dimension, and they'll calculate how they have to initialize it such that sort of the total norm of a random vector that goes through stays the same. The vector would go through, like it would go in here and out there. So you see, if it changes dimension, then if you just randomly initialize with all the same, like every matrix with the same number, then like with a normal distribution, then in this case the vector would gain in norm, and to account for that, you initialize the matrices such that the vector norms approximately stay the same. And this is why there are different initializations here. And you can see this at the end of the training. Now, these in different layers right here, it's pretty much always the same pattern. Now they say, they just remark it. So this is what I find weird. They just say what the graphs show. They don't interpret it. Like, I would expect something like, oh, this pattern is exactly what we would expect from our model because something, right? Like if they claim that this attention is being able to be learned, I just don't see why they do this stuff. They simply point out, oh yeah, this is higher here and this is higher here. But I don't even see that as too interesting, given that this is how you initialize it. Like if I shift everything to the left a bit, and this is a wall, so it like this piles up here, then this is exactly what turns out. I don't see what this is supposed to mean, especially since they don't make any claim of what it is supposed to mean. And the same here, they say the effect of the number of heads. Okay, we investigate the effect and the number of heads on the random synthesizer models, and they train the number of heads. Now, somewhere in the text, they say, I remember, they say, since we don't dynamically route, it is very important for our models, very crucial to have many attention heads, right? Such that basically you don't have one routing pattern, you have many routing patterns that you learn globally. So they say it's very important for our model to have many attention heads, and I guess that's what they're trying to demonstrate here. But again, they simply say what's happening, they don't interpret it, and they don't compare it to anything. They just put it here. They just put the number, and I don't like, is this good? Is this bad? Can you compare it to something? And also here in the original paper, they do the same thing here. As you can see, the number H is the heads, and they do ablate this, but at the same time, they adjust the dimensions of the key and value vectors such that in total, they have the same amount of parameters, right? So they can really investigate, is one big attention head better or worse than many small attention heads? Is there a trade-off? And they find here that there is a bit of a trade-off, like there is a sweet spot. You don't want too many, you don't want too much because they get too small, something like this. But first, we don't know whether or not have they simply changed the heads but left every other parameter the same, or have they also adjusted the dimensions? Because if they haven't adjusted the dimensions, then this increase would be absolutely expected because you now have more parameters. And if they have adjusted, then can we compare this to something? Because this is the T5 small. This is not the original transformer. Like, is this big? Is this small? And what does it say about the claim that you made that the number of heads is so important for your model? Can you validate this using this? So it's just a bit of like this entire page here. It's just they just measure some things and then they state them here, and you're somehow supposed to guess what they mean by stating that here. Okay, but that was enough for me ranting. So they give some supplementary material right here. But in essence, what I like about the paper is sort of the thinking that goes into this, thinking outside the box, asking the fundamental questions about these models. Do we really need this? What do they do? I don't think it's super well investigated really from a scientific point, like the formulation of hypotheses. It simply trains these things and then makes some claims, but the claims interact, with the number of parameters here and so on. So and they're sort of noisy all around. And of course, the fact that this thing here turns out to be a fully connected layer in disguise is also pretty funny. But I get it. It's it's not exactly the same thing, but yeah. All right, so that was my take on this paper. If you have a different one, let me know in the comments for sure. I read all of them, and at least I try, and have always succeeded so far. All right, I'll see you next time. Bye-bye.